Hello and welcome to another episode of Disseminate, the Computer Science Research Podcast. I'm your host, Jack Waudby. Today's episode, we are going to be talking about a few things. We're going to be talking about stream processing, the Internet of Things, and fault tolerance. And joining us in that chat to tell us all about her awesome research is Anastasiia Kozar, who is a PhD student at the Technical University of Berlin. Welcome to the show, Anastasiia.
Thank you, Jack. It's really nice to be here. Thanks for the invitation.
Cool. Well, let's jump straight in. So can you start off by telling us your backstory, a little bit more about yourself and how you became interested in data management research?
Yeah, so as you've mentioned, I am a fourth-year PhD student at Technical University of Berlin. I completed my master's at Otto Friedrich University of Bamberg, which is in Bavaria, in Germany. And there I got inspired by my professor, Daniela Nicholas. Big hi to Daniela. She was a professor of databases back there, and I somehow got the best grade, and the lectures were so interesting. And then she asked me also if I'm interested in a job. So I got invited as a research assistant to her faculty. And I started working on IoT actually directly. We had like a large scale installation of like cattle related IoT devices. So we were analyzing behavior of cows in Bavaria and trying to predict what they are doing at specific moment of time. For example, drinking, eating, sleeping. Yeah, so that was my research. And then we had a chat with her. I told her that after my master's, I would be interested to like proceed the academic experience or like to work further on that. And she provided me with like a list of options where I can get the PhD, well, specifically in Germany, to be fair. And the first one was Berlin. So I passed like a few interviews and got accepted to Technical University. And now I'm working with Professor Volker Markel. Yeah, and I'm really happy to be part of this faculty.
Awesome. So what do cows spend most of the time doing? That's the first question. Yeah.
Eating.
Yeah. That's something me and cows have in common. That I guess I also spend a lot of my time. But it's funny. We also share the same thing. That my master's project was also on cows. So mine was also all kind of cows and sheep and things. But it was to do with the spatio-temporal analysis of salmonella and I can't remember the title now. Antimicrobial resistance, that sort of stuff, and trying to work out how it spread. It was a long time ago now. I've forgotten most of the stuff. But yeah, I also did my master's related to cows. So yeah, we've got something else in common there as well. Cool. So yeah, as I teased at the top of the show, today's topic is stream processing, the Internet of Things, and fault tolerance. So let's set a little bit more context for the chat so the listener knows what all these things are. Tell us, what the heck is the Internet of Things? And what is a stream processing engine and fault tolerance? Yeah, introduce all these topics for us, Anastasiia.
Yeah, sure. Well, so the Internet of Things, I think it's a really common term nowadays. So there is no like really strict definition, but it's basically a bunch of devices that are interconnected by a network. It's not necessarily even internet. They could be interconnected by some kind of local network. In most cases, they are also connected to a cloud. So it's like unified, something like sensor edge cloud network all together, where we have really many different types of devices. There could be small sensor devices, intermediate edge devices, large scale servers like in cloud. So that's what we mean by IoT. And do we mean by stream processing engine in relation to the IoT is that the sensors that are normally located somewhere, for example, geodistributedly located somewhere in the field, they send data, they submit data with like really high frequencies, and these frequencies have to travel from the sensor devices through these edge devices to the cloud. And normally, In most cases, the users then talk to the cloud and can retrieve the data, work on it, process it, analyze it, and do whenever they want to with the data. Yeah, so this is a context of IoT in relation to the stream processing.
Awesome stuff. Yeah, it's everywhere these days, IoT, right? I mean, everything's connected to the internet, your fridge, and it's crazy. You're getting more and more connected. There's some crazy numbers in your paper at the very start, actually, about sort of the volume of devices that will be connected in the internet against by this. I can't remember the exact number. Maybe I've got it next to me. I can pull it up here really quick, but 27 billion by 2025. So wow, it's a serious volume there. Cool. So given all this context then, obviously you and your colleagues at TU Berlin, you're working on an IoT data management system that's called NebulaStream. So can you tell us a little bit more about, I think this is a collaboration as well with a few other universities, I think, right? The whole project. Yeah, so tell us more about NebulaStream and what's going on there with that.
Well, so the original idea of NebulaStream project was to process this data that is passing from sensors towards the cloud on the way. So basically, there was a paper on CIDR where we ran a couple of experiments and found out that sending all this large amounts of data that are produced by the sensors to the cloud somehow introduces a bottleneck at the cloud when it starts processing these amounts of data. So it's sometimes profitable to push down the computation to actual smaller devices. I can give an example so that it will be easier to get it. For instance, if we have a query which has to filter a temperature, let's say temperature less than 22. And then there are a bunch of sensors deployed. We don't need to send all the temperature values to the cloud to distract to all this temperature that is less than 22 degrees. We can just subtract this data directly at the sensor and send only the data that we actually need. So it will reduce a lot the network usage, and it will also save some resources for us at the cloud to actually enable like more continuous computation. So
so you referenced the CIDR paper there. Just for the listener, what's that paper called in case they're interested? And I'll drop a link to it in the show notes as well. But if you can remember what it's called.
It's actually called NebulaStream, but for everyone who is interested, we have a website called nebula.stream.io, and the paper is called the NebulaStream Platform, Data and Application Management for the Internet of Things.
Awesome stuff. So given this NebulaStream then, and your research focuses specifically on sort of in this context fault tolerance, right? So and you recently published, this is why we're trying to say, a paper at SIGMOD this year. So can you give us the overview or the problem statement of your actual research here and what you're actually trying to achieve? Yeah.
So basically, because we are having processing on this smaller devices that are also unreliable, plus the network can be unreliable, it's important to make sure that we are handling failures in case they happen. So for instance, as you mentioned before, that we are having partners. One of our partners is Charité. I don't know if you've heard of it. It's the largest research hospital in Europe. And they have their ICU units, which is intensive care units, and the patients that are lying there, they're getting constantly analyzed in terms of their heart rate, their temperature, their whatever vitals that are necessary for the analysis. And the idea there is that if we would apply NebulaStream there, it's crucial for the life safety of the patient that no data is lost and all the data is getting processed. So my topic is about how to make sure that we don't lose any data in case the data was set by user to be really important and necessary. That could be many solutions. One of them I actually discussed in my paper at SIGMOD 2024.
Cool. Yeah. So given this then, tell us a little bit more about what is problematic at the moment and what you're actually trying to achieve with your research, in the sense of, okay, so fault tolerance is really, really important. We need this because obviously it can cost lives if we don't look after our data correctly, right?
Yeah.
So how has that problem been approached in stream processing engines at the moment, and what is the problem with that, or the way it's been done at the minute?
Yeah, so the problem is that most of the fault tolerance solutions were developed for the cloud, because mostly stream processing engines were developed for the cloud. So they do not have this assumption of devices being heterogeneous, meaning that they do not consider that resources can be limited. They assume that we have like virtually unlimited resources as cloud has. Also, that network is reliable while we are having unreliable network. Yeah, these are the main restrictions that we are focusing on, and that makes the solutions inapplicable towards our use case.
Yeah, you give a really, maybe good to maybe illustrate this a little bit further. You actually you give a really nice example at the start of your paper as to why, or then to give some numbers, some kind of put some values on why, how problematic this can be if we don't factor in fault tolerance correctly. So maybe you could tell us a little bit more of that sort of experiment you did to illustrate this point.
Yeah. So the experiment that I highlighted in my paper was I actually took a Raspberry Pi, which was a really limited amount of memory. It was 1 gigabyte available. And I deployed Flink there and I started submitting queries. But first I started submitting queries, stateful queries that require intermediate processing. So in terms of Flink, I computed Medium, which required additional memory. And I started submitting these queries to this Raspberry Pi nonstop, until the point where Query Optimizer basically told me that, okay, we are out of memory, sorry, you cannot deploy more queries. These were 35 queries. And then I said, okay, well, 35 queries is not bad, but what about if I actually start running fault tolerance in the background? So I deployed everything completely the same, but I also asked Flink to enable fault tolerance. They have checkpointing algorithm. And I again started submitting these queries. And after the 27 query, I completely killed the device until it started being irresponsive. It took me 2 hours to bring it back to life. And of course, Flink hasn't noticed that something is wrong because nowadays, unfortunately, query optimizers do not take fault tolerance into account. They are really well tailored for resource analysis in terms of processing, in terms of different kinds of workloads, but they do not care about fault tolerance, and they kind of think that it's something that is getting run in silo and does not require analysis.
It's quite a serious drop off, right? Going from sort of 35 down to 20, mid-20s queries. It's a significant drop off when you actually, you need fault tolerance, right? From what you said earlier on about in certain examples, certain cases, we have to have this property. It's really important. We can't lose our data. There's no point in being fast if we lose all our data, right? So yeah.
Exactly.
So given this experiment you ran, and then how did you formulate this problem that you wanted to solve?
Well, basically the problem was that, there were 2 sub-problems actually of the problem. The first one is that we deploy fault tolerance by default on every device of the system, independently of the resources, independently of the user preferences. Fault tolerance is run by default everywhere. And second problem, even though it's run everywhere, it's cost not getting analyzed and included in any decision making. So we know that every device is participating in an algorithm that requires additional resources, but we never analyze these resources and assume that it's just enough of them at some point. So of course it results in a big problem in terms of systems with limited resources and with small devices, especially participating there.
Cool. So let's talk about the solution then, Anastasia. So how did you go about solving this problem?
So first of all, I actually look at this solution from the perspective that we don't need fault tolerance by default being run on all the devices, especially considering the IoT installations, which could include thousands of millions of devices. Running fault tolerance on every device for one query is a bit too much. So my idea was that we allow user to choose the importance of the data per query basis. And then once the query is, the client receives this query request at the master node or the coordinator node, which is run on the cloud, it analyzes all the available devices and it first makes a decision on fault tolerance basis. So before deploying the processing operators, before deploying the query, it first decides where are the optimal places for fault tolerance to run, and then deploys processing operators only on the devices that were chosen to be reliable enough and that were chosen to be to participate in fault tolerance. That being said, sometimes, sensors, if we need a specific sensor, like it was an example that I gave to you about the temperature, let's say we need a temperature at the sensor number 22, so we cannot choose there a lot. However, there is still a path between this sensor and the cloud, which includes possibly multiple edge devices. So not all of them can participate in fault tolerance due to several reasons. Some of them can be that it's out of resources. Some of them can be, I actually include in my analysis also individual reliability of the device based on like manufacturer property of the device. So sometimes it's more profitable that the more reliable device participate with the less resources involved in processing. So we do kind of the smart decision, and then we allow Query Optimizer to deploy processing operators on chosen devices. So overall, we basically change the priority of how we deploy processing operators, like stressing out that fault tolerance is more important than the processing, as you pointed out, that speed is not so important if the device has failed.
Yeah, right. So it's kind of moving fault tolerance up to being a first class citizen, right? In the way you think about your data, thinking about your system, which is really nice, and kind of having the ability to have users express that and capture that is really nice. So, and it's quite a complex optimization problem, right? So you approach that, tackling that kind of optimization and figuring out where to put things, to put fault tolerance in sort of in. There's the two sort of, maybe there's three, I think, actually. There's the single objective optimization and then the multi-objective optimization, right? And there's one that has sort of the dynamic aspect to it as well. So give us a rundown of the different approaches we can kind of take to solve this optimization problem.
Yeah. So, well, the single optimization basically is easy. We either fix fault tolerance level or we fix resource utilization, and then we try to either maximize the reliability, so the fault tolerance, or we fix fault tolerance and then we try to minimize the resource utilization, which is like a standard thing. And then a multi-objective optimization is a bit more complicated. There are several approaches developed for this. Many of them are used by Query Optimizer nowadays for processing operators. So basically, my takeaway there is fault tolerance can be represented as an operator, as just a processing operator, basically, with also its own needs, its own costs. And then we could use any of existing multi-optimization strategies or approaches to actually make a placement decision, which is, well, NP hard. So, yeah.
Cool. I just wanted to dig into a little bit more detail. I don't think we actually covered it off yet, but the various different fault tolerance approaches you actually can have in this system. I'm not sure if we've gone into them into a few detail. I think there's upstream backup, passive standby, and active standby. So maybe we can tell the listener about those different strategies so they can kind of maybe visualize how fault tolerance is actually achieved in practice a little bit clearer.
Yeah, sure. So basically, there are three main classes of approaches that I would say. The most easy one is an upstream backup, which is basically buffering. So before sending the data to the next device, we just buffer the data. And in case next device fails, we will just resend the data. Then there is an active standby, which is basically sends data on parallel paths, enabling parallel processing. And in case device on one path fails, then we still ensure that data is getting delivered because there is an alternative path running. And then there is checkpointing, which makes like a snapshot of the entire data and including the state of the device and sends the state or like snapshot somewhere, either remotely or stored persistently, like different system implement this differently. However, the main point here, what is more important in terms of IoT and IoT-based stream processing systems, is that all of them kind of need to save the data, well, obviously, so that it can get replayed or resent in terms of failure, but it cannot store all the data because, well, streams are infinite. So we cannot store all the data. We have to delete it from time to time. And we cannot just delete it from time to time. We cannot say, okay, please delete it every 2 seconds and it will be fine, because we don't know which data has reached the user. And the data reaches the user when it reaches the cloud, and cloud actually gives it away to the user. So what we need to communicate to the cloud, to the coordinator or master node, and ask the master node, okay, can you please send me what data is safe to be deleted? So this communication requires some time, and there is some delay time, and this results in additional cost that fault tolerance requires. So it obviously, the more often we ask master node what can we delete, the less data we store, but the more network we need, because we just more frequently send this question message or like acknowledgement message. So there is a trade-off in between resources for every presented fault tolerance approach that right now exists, just because of the specifics of the IoT.
Nice. So going back to the optimization problem. So we've got these different approaches we can actually use in our head now, and revisiting this resource reliability sort of trade-off space we want to optimize along. And how do we actually kind of go about then estimating what fault tolerance costs?
Yeah. Well, so as I mentioned, the main hyperparameter here will be the streaming frequency. So how often do we delete this data that we actually store? And nowadays, most of the system let it live like a hyperparameter. So they say, okay, I let the user choose how often, or it's just a constant variable that is set in the system for system-wise, which is, not really optimal. In my paper, I ran a couple of experiments in the evaluation part, showing how important it is actually to set this parameter correctly, how crucial it is for the system, because sometimes just choosing the parameter wrong can result in system becoming out of memory just because of fault tolerance. So because not a lot of processing. Yeah,
it's crazy, right? It's kind of the systems, in a sense, kick the can down the road and make it the user's problem, right? It's you worry about this setting, I'm not going to, and then they kind of absolve themselves of any responsibility of setting it properly, which is the easy way out, right? Which is not ideal. Cool. Yes, I don't know if do we have anything else we want to dig into a little bit more on the cost estimation sort of angle, or should we talk about some solutions and the actual different placement strategies you developed?
I think, we are done. Basically, there are three costs that I considered. These were processing, network, and memory. Processing cost does not quite change. I mean, I ran a couple of experiments and it didn't show any real impact there. However, for example, in terms of active standby, because we have to process on parallel paths, so we would have to deploy redundant processing operators that would just double the processing cost basically for us. And network memory trade-off, I already mentioned, it comes from the storing data and the requirement to delete this data periodically due to the memory constraints, because we cannot store all data since we have infinite streams. Yeah.
Cool. Well, in that case, then tell us about Naïve fault tolerance placement and multi-objective fault tolerance placement, and then the one with the hyperparameter as well, which I think is I like that one the most, I think, because I like it. I don't know why, actually, because I like it when things are dynamic, right? And you can oh, cool. Yeah. Anyway,
right.
Sorry. Yeah.
So, the Naïve one is the Naïve one. We say that, there are, for example, I got inspired by the existing query optimizer strategies. So there are multiple placement strategies there. The first ones and the simplest ones, heuristics based, which say, oh, okay, we have a processing operator, it needs one slot, whenever slot means in the system. So, and we say that, we have a device and it has, let's say, 5 slots. So we know that there are 5 slots, we know the query, we know the number of operators we want to deploy to the device. So we kind of have this theoretical estimation of resources on the device. And therefore, my Naïve strategy was to say, okay, fault tolerance also needs 1 slot. So here we go. We don't only need 1 slot for the processing operator, we also need 1 slot for the fault tolerance. However, when I ran the experiment with this kind of estimation, so first of all, I repeated the experiment with Flink, with Raspberry Pi and Flink, but with NebulaStream and Raspberry Pi. And in terms of NebulaStream, I was able to deploy 64 queries without fault tolerance and 42 queries with fault tolerance. And 42 queries, again, of course, killed the Raspberry Pi, so I killed it twice. Yes, I did it. So, and with Naïve estimation, saying, yeah, one slot, processing one slot, fault tolerance, since we deploy 64 queries without fault tolerance, we were able to deploy 32 queries with fault tolerance, because now instead of one slot, we needed 2 slots every time. So we decreased the amount of query by double, 32, but we did not fail the Raspberry Pi, which was good. However, we knew that we could actually deploy 42, because at the 42 queries, the Raspberry Pi died the last time. So we knew that, well, the estimation is not really precise. We could do better than that. And then I started looking at this memory network pattern, and I calculated that, for example, we have this hyperparameter like trimming frequency. So how often do we trim? Let's say we trim every 100 tuple buffers, or like buffers. And let's say we know the size of the buffer, because normally we know it. It's configuration of the system. So we can calculate approximately how much memory we will need at the point of time. So we will store for fault tolerance 100 buffers. Let's say each buffer 1 kilobyte for the simplicity. So we will need 100 kilobytes whenever. And then after that, we will send message to the master node, and master node will reply to us. And there is still this delay of not knowing how much actually memory will it cost us to actually wait for this message to reach the master and reach back. But well, knowing the network delay and approximate like number of hops, we can still predict that, and this estimation is kind of safe there. So having this estimation, we reached actually 42 queries, but without failing the Raspberry Pi, which is good. So it was originally targeted amount of queries, but we did not even kill the poor device, which was good. But then I still went further and I said, okay, well, but actually we could notice that we are getting out of memory at some point, and we could switch to start sending more often these messages for deleting the memory, for cleaning the memory. And like that, we will utilize more network, but we will save more memory. And having this optimization, I reached 56 queries out of 64 original, which was like actually a major result in terms of, number of queries deployed.
That's awesome. I mean, I was at the start, I was saying they're going to stop you from buying Raspberry Pis if you keep killing them. But
I hope they don't have my name on their red list or whatever.
But it's really nice to see that iterative process as well, as kind of as you went through doing these experiments, you were kind of like, oh, well, actually, I can maybe tweak it this way, or I can go this way and do this little action. So it's really nice to see that iterative process sort of play out and see, because I mean at the end you always I just read the research paper, right? It's like you had idea 1, idea 2, idea 3, and they all just came to you at the same time. But it's nice to see that sort of iterative process play out there as you did these experiments, and to see the gain each time must have been a nice experience from you for you as well. Cool. So I guess given that we touched a little bit there on sort of results and a few numbers and stuff, but maybe we can talk about your experience in a little bit more depth. So yeah, overall, how did you go evaluating all of these different approaches you developed? Yeah, and what data sets did you use? Who did you compare against? Obviously, Flink and NebulaStream were used, right? But yeah, tell us more about your experiments is the question I'm trying to get to, Anastasiia.
Yeah, sure, no worries. Well, so the first experiment I basically brought you as an example in terms of how I came up with the different solutions. So that's exactly the same measurements, but for 4 Raspberry Pis, not for 1. So you can just multiply these values by 4, and that's how you will get my first estimation. Then I actually looked at the resource consumption to see that actually, Naïve approach is not really good at resource estimation, because it just says, uses some kind of slots. Who knows what slots mean, how many slots a Raspberry Pi has, and it's a bit like, heuristic approach. Then we actually also, in the resource analysis, I think we see how Flink failed, why it failed. It went out of memory, which was according to the initial assumption. Then I ran a scalability analysis. Basically, I actually use Kubernetes for that. I used Google Cloud with up to 256 devices, I think. So I basically allocated 256 Raspberry Pis and use Kubernetes and Docker image to deploy them on every instance. I wanted actually to run 512, but then Google Cloud wrote me a sad message saying that I'm already utilizing all the CPU of Western Europe, so they cannot give me more. So I had to stop at 256. Yeah.
Yeah. They need bigger data centers, is what we're saying here. Right? This is a call to action for Google: build more data centers. Yeah, no.
I'm actually a bit worried how many companies have me at their red lists, like of not giving me any more devices or hardware resources. Yeah,
Cool.
and well, the analysis that I find cool is actually this hyperparameter analysis, where I tried like different trimming frequencies and see how they influence the system and what happened. Because, well, what can I say is that if we don't trim the data in time, we just can, well, we will be running out of buffers, because normally how system works, they allocate a pool of buffers at the launch, and then this buffers from this pool are getting used inside the system. So unless the buffers are getting trimmed, they're still stored in the systems, and they cannot be used to retrieve new data to actually send it further. So if we don't trim enough in time, we can be at the point where we don't have any more buffers, but we still haven't sent the message to the master node asking to delete the buffers. So we are just stuck at the moment where we are constantly waiting for new buffers, but never actually freeing any of the buffers. So I would say it's a crucial parameter, and it's really important to choose it wisely.
Yeah, to choose that parameter, it's obviously how is best to make that decision? Is there sort of a way we can pick that in a manner that will always guarantee we don't hit this problem of not having any space to get the message back to us to then be able to trim it, right?
Yeah, I actually believe that the optimal value can be calculated using my formula of memory estimation for fault tolerance. So basically, if we say like amount of buffers plus the delay of both sides of trimming message, that should be a really valid formula to use if we want to estimate this value.
Yeah, I just wanted to double check my understanding as well of that. These fault tolerance placement schemes, is it a deterministic guarantee that we will never ever end up being under provisioned again and or anything like that? Or is it just a best effort? We could possibly still hit an
Yeah, so there is a basic problem in the IoT with processing guarantees so what you've mentioned right now, these are processing guarantees, and different systems support different guarantees. For example, the strongest one is exactly once, meaning that we do not lose any data and we do not produce any duplicates in case of a failure. Then there is at least once, which is we don't lose any data, but we might have duplicates. At most once that we lose data, but we don't have duplicates, and then none. And so the problem of IoT is that because the data is getting produced at the lowest devices, in case the producers of the devices, like the sensor device itself, fails, there is no way independently of my fault tolerance approach that I can reproduce this data, because it's the producer who failed. So I say in my papers that we start working from at most once. So unfortunately, at least once and exactly once is not achievable for us. So we have different flavors of at most once. But answering your question, no, you cannot be sure that your data will get delivered, because in case the producer will fail, then there won't be any data to deliver. Otherwise, yes, there won't be so there will be a probability with which the data will get delivered. I create several classes just to say that there is high probability, medium probability, and low probability, just so the user wouldn't have to use, the number between 0 and 100, but have these classes of oh yeah, I want really badly my data to get delivered, so then it's high.
Cool. Yeah, I guess that's really interesting. I guess kind of leading on from that, then it's kind of, I always like to ask about limitations of various solutions. I mean, this is a massive improvement over the state of the art, right? And kind of just not thinking about fault tolerance over the at all. But I always like to kind of ask and sort of probe a little bit about limitations. And are there any situations? Obviously, this is the fact that we can't have exactly one semantics. It's kind of out of our control, right? It's just the facts of life in a way. So we have to work around that.
Yeah.
But are there any sort of situations or scenarios in which the placement strategies end up being suboptimal?
Well, there are multiple. I mean, so basically, I am not the inventor of placement, right? I'm just using the placement algorithm, and I also treat fault tolerance as a black box. So I basically say, yeah, any fault tolerance approach is an operator, and I just deploy it. So I'm just, don't take any responsibility. I'm serving as a bridge between the query optimizer and the fault tolerance guys. But of course, there are several sub-optimalities there. I mean, I used in my paper, for example, weighted sum algorithm, which is, well, considered to be suboptimal in terms of multi-objective optimizations. We have the weights. These weights are again chosen by either the developer or the user saying, oh, okay, our system is memory restricted, or our system is lacking network bandwidth, or whatever. Yeah, so in this sense, we are restricted. What else? We are also, of course, restricted that if we have just many unreliable devices, that wouldn't matter actually where we deploy fault tolerance, because probability will be everywhere the same. So yeah, I mean, there could be many examples, but the major idea, I think, is still there. Just trying to help avoiding the problem of like fault tolerance running in silos. And
yeah, for sure. Even the natural next step for your work on fault tolerance in the Internet of Things, and in NebulaStream.
Yeah, so as I just mentioned in the evaluation, I highlighted that there is a problem with scalability. Did I mention that? Maybe I should mention that I actually found out that there is a small problem with scalability with any of the approaches, just because of this trimming patterns that we have to ask somebody and we have to wait. So there are two problems. The first one, if we have really long pass in between the last device and the master node, so there will be really many hopes to jump in, and at some point we cannot find like optimal amount for buffers to get stored, because the optimal amount is less than 0, which is like, obviously we're just not managing to trim data fast enough. And the second problem is that master node is serving as a like central unit, which is doing really many parallel processing. So if we have also really many pass, then the master node is struggling answering all these questions about which buffers are safe to trim. So these are two problems. And my future vision of this problem is to actually move from the centralized architecture in terms of fault tolerance to the decentralized one. So a bit like peer-to-peer inspired, where each worker is taking responsibility for himself and talking to the neighbors, maybe like analyzing neighborhoods. And yeah, this is also the idea of my papers that I'm currently writing.
And a teaser, yeah, for the listener to keep their eyes peeled. There's more work coming soon. It's interesting you those future directions, because I was kind of thinking about this, and so like you said, there's the network topology is in a way that makes the scalability be a problem, right? Is that if you have, how much of a control do you have over the network topology and which devices are connected to each other, and how much do you have to just assume that's a given, or do you have a control over the whole architecture of it? So, okay, well, if we connect these devices, that's going to then make the whole picture a lot nicer. If we can connect A and B, then that's going to make all our problems go away. Like, how much control do you have over that actually, or how much do you just assume that the network, the hardware and the way things are connected is just a given, and we're just going to try and work on top of that platform?
Yeah, so at the moment in NebulaStream, we have like coordinator running in the cloud that has an understanding of the global topology. And we kind of have this assumption of the worker running in isolation without knowing the global topology. So all the optimization decisions are made by the coordinator. It then propagates these decisions to the workers partially, and the worker then performs. Well, in our case, we are compiling this query to run it really efficiently, to utilize resources really efficiently. But yeah, so we have this isolation assumption.
Nice. It'll be really interesting to see how your work progresses in this area as well, and see how NebulaStream progresses as well. And cool. Yeah, let's talk about that a little bit more actually then, about impact. And obviously, I don't know how widely used NebulaStream is outside of sort of as a research vehicle, or if it's used at all in any sort of production setting. But has your kind of work on fault tolerance had any impact at the moment, or what sort of impact do you think it can maybe have in the future, and maybe be incorporated into systems like Flink?
Yeah, well, so I find NebulaStream conceptually a bit different from Flink. So it's like one can say a next generation of a system after Flink. And what I say is that the algorithm I develop is like targeted more towards this like device setting with limited resources. So Flink is running in the cloud, so they basically don't care about this. But potentially, I think it's a major improvement in terms of, well, not only reliability, but also of understanding the nature of fault tolerance, understanding the costs of fault tolerance. I think that if, for example, an engineer will have to set up a large installation of IoT devices, my paper will help understanding better how much resources, estimate, for example, how many devices are needed for the system, how many resources the system has. And knowing also the use case, for example, we know that the installation is with sensitive data or with like important data. We could estimate overall, like, yeah, the amount of devices. Basically, we don't like blindly buy, like, let's say, thousands of devices and assume that, yeah, it will be enough, but we can actually perform some kind of smart analysis for this decision making. Yeah.
Nice, yeah, some data-driven decisions, right? I think is the kind of catchphrase for it. But cool, yeah. So I guess my next few questions are more about sort of the not the non-technical stuff, but the stuff that happens along the way and the journey of when you're working on a paper like this. And the first one is, whilst working, I mean, maybe not specifically on this paper, but maybe on your PhD studies at large, what's been the most interesting thing that you've kind of learned so far on that journey?
Well, I guess I kind of enjoy working with different types of hardware. So as you might have noticed,
you like destroying different types of hardware.
Yeah, maybe I enjoyed a bit too much destroying different types of hardware. That's true. Including my laptop a couple of times. But Yeah. Well, but to be honest, yeah, before that, I didn't have any experience with like raw hardware. I had to manually connect Raspberry Pi, create like local network. I also got to know like Kubernetes, Docker, and all this kind of infrastructure. So it's like a first-hand experience that I got there, which I've never had. And also what was interesting for me and is still interesting is to be part of like a larger team where we are all researchers contributing to what we are trying to build as an industrial project. So yeah, that's also something new for me and something that I experienced during my PhD. Well, of course, freedom of decision making. That's exactly why I came here, and that's exactly why I'm doing my PhD, to have this freedom and to actually have an impact in the future somewhere, hopefully.
Yeah, I'm sure you will. I guess going off that, I mean, segueing from that last bit about having that freedom to pursue your own ideas and to kind of get creative. And maybe you hinted at, maybe I kind of got an idea of how you work later on, and you said you kind of did this experiment, then you tweaked it this way, then you tweaked it this way, and you kind of ended up sort of developing this solution space. But yeah, how do you go about generating ideas? What's your creative process?
Yeah, I actually thought about that a bit, and I think that I like visiting different talks from different people, listen to the current research. We have plenty of visitors that give like keynotes or talks, also industrial partners, for example. And somehow during these talks, I get extra inspired. So I keep my notes on my iPhone open and I just write down some ideas for my own paper. Sometimes I actually even skip like part of the talk just because I'm so into my own ideas that I kind of get distracted about that. But yeah, I would say this is my major resource of motivation.
That's a nice approach, kind of that. Yeah, I've had people before who've answered this question. They're sort of like they've mentioned this idea of having of kind of breadth and borrowing ideas from or seeing the way people approach problems in other domains or even within the same space, but kind of like closely related. Maybe not even not biology, maybe, but just kind of a different field within computer science. And there's a lot of parallels that can be drawn between the two, and you can take ideas from those and give you. It's a nice way to sort of generate ideas, which is cool. So I guess we've made our way all the way to the last word. But before we do that, I don't know if you saw in my email about the possibility of giving the listener a recommendation.
Yeah, I saw it.
This is a new feature, Anastasiia. So
Okay.
you got the honor of delivering the listener the first recommendation. Or the recommendation can be anything tech related. It can be a blog post, a paper, a new system, a new tool, or something that you've encountered recently that you thought the listener might enjoy. So yeah, what do you have for us, Anastasiia?
Yeah, so first of all, please do not destroy your hardware that you're actually supposed to use for the evaluation. But that's just a general recommendation. But I thought about it, and I think I would recommend to try out NebulaStream, of course, because I am the first hand experience here. And we plan open source release on SIGMOD 2025. So it should be released this year. Well, next year, right? And right now it's also available, but only for research. And we are also having our small communities where we support people that try to do stuff with NebulaStream. So people should not be scared to use it. We will support everyone. And yeah, I highly motivate to play around with it.
Fantastic. And correct me if I'm wrong, but that's kind of quite nice because SIGMOD is in Berlin, right?
Yeah, that is correct.
There we go. There's a perfect alignment there.
We are hosting this year, yes.
Yeah, so it's a celebration. Cool. So yeah, now last word. What's the one thing you want the listener to take away from this podcast, other than your awesome recommendation? But yeah, one more thing from the last word to finish us off.
Well, so if you're in a database communities, that I would highly recommend not to ignore fault tolerance and think of it beforehand and think of it all the time, as it is really important. And of course, if you're a PhD during your work, I would generally recommend people to take that time, enjoy the research part, enjoy the freedom of the decision making and choices, and try to change something, try to change the world and impact the research community somehow. That's, I guess, the most pleasant part of the PhD, in my opinion.
Awesome. So that's a great message, Finn. I'm +1 with you for you on the fault tolerance. I agree with you on that one. Yeah, very important. We've got to look after your data. It's been a really nice, really enjoyable chat, Anastasiia. It's been lovely talking to you, and I'm sure the listener will have really enjoyed the conversation as well. We'll put links to everything in the show notes, so the listener, you can go and find and play with NebulaStream and read all of Anastasiia's awesome work. We'll put links to there and everything in the notes. And yeah, we'll see you all next time for some more awesome computer science research.